enums and pattern matching. In this chapter, we will look at enumerations, also referred to as enums. Enums allow you to define a type by enumerating its possible variants. Enums allow you to define a type by enumerating its possible variants. Define a type by enumerating its possible variants. First, we will define and use an enum to show how an enum can encode meaning along with data. Next, we will explore a particularly useful enum called option, which expresses that a value can be either something or nothing. Then we will look at how pattern matching in the match expression makes it easy to run different code for different values of an enum. Finally, we will cover how the if-let construct is another convenient and concise idiom available to handle enums in your code. Finally, we will cover how the if-let construct is another convenient and concise idiom available to handle enums in your code. Okay. They will look at how pattern matching in the match expression makes it easy to run different code over different values of an enum. Defining an enum. Where structures give you a way of grouping together related fields and data, like a rectangle with its width and height. Enums give you a way of saying a value is one of a possible set of values. Where structures give you a way of grouping together. Related fields and data, like a rectangle with its width and height. Enums give you a way of saying a value is one of the possible set of values. Give you a way of saying a value is one of a possible set of values. For example, we may want to say that rectangle is one of a set of possible shapes that also include circle, and triangle. To do this, Rust allows us to encode these possibilities as an enum. We may want to say that rectangle is one of the set of possible shapes that also include a circle and a triangle. To do this, Rust allows us to encode these possibilities as an enum. Let's look at situation we might want to express in code and see why enums are useful and more appropriate than structures in this case. Say we need to work with IP addresses. Currently, two major standards are used for IP addresses, version 4 and version 6, because these are the only possibilities for an IP address that our program will come across. We can enumerate all possible variants, which is where enumeration gets its name. Any IP address can be either a version 4 or a version 6 address, but not both at the same time. Any IP address can be either a version 4 or a version 6 address, but not both at the same time. The property of IP addresses makes the enum data structure appropriate. Because an enum value can only be one of its variants, both version 4 and version 6 addresses are still fundamentally IP addresses. So they should be treated as the same type when the code is handling situations that apply to any kind of IP address. Any IP address can be either a version 4 or a version 6 address, but not both at the same. Okay. The property of IP addresses makes the enum data structure appropriate. Okay. Because a enum value can only be one of its variants. Both version 4 and version 6 addresses are still fundamentally IP addresses. So they should be treated as the same type when the code is handling situations that apply to any kind. Okay, makes sense. So any kind of variants in the enum, they are the same types because they have to be considered as the same type to deal with the data. Uh, Makes sense. So we can express this concept in code by defining an IP address kind enumeration and listing the possible kinds an IP address can be. V4 and V6. These are the variants of the enum. IP address kind is now a custom data type that we can use elsewhere in our code. Enum values, we can create instances of each of the two variants of IP address kind like this. Note that the variants of the enum are namespaced under its identifier. Note that the variants of the enum are namespaced under its identifier. Note that the variants of the enum are namespaced under its identifier. Variants of the enum are namespaced. Variants of enum are namespaced under its identifier. And we use a double colon to separate to separate the two. This is useful because now both values IP address kind v4 and IP address kind v6 are of the same type. This is useful because now both values IP address kind v4 and IP address kind v6 are of the same type. IP address kind, we can then, for instance, define a function that takes any IP address kind. Wait a second. Note that the variants of the enum are namespace under its identifier, and we use a double colon to separate the two. This is useful because our both values v6, v4, and v6 are of the same type. Okay, that makes sense. I will just kind of we can then, for instance, define a function that takes any IP address kind. Makes sense. And we can call this the function with either variant, v4 and v6, passing it. Okay. Using enum has even more advantages, thinking more about our IP address type. At the moment, we don't have a way to store the actual IP address data. We only know what kind it is. Given that you just learned about structures in chapter 5, you might be tempted to tackle this problem with a struct as shown in listing 6-1. Listing 6-1, storing the data and IP address kind variant of an IP address using a struct. Okay, struct and IP address and a kind. Oh, IP address kind. We can make it even. Okay. Interesting. Storing the data and IP address kind variant of an IP address using a okay. Storing the data and IP address kind variant of an IP address using a struct. Okay. Here we've defined the struct IP address that has two fields, a kind field that is of type IP address kind. The enum we defined previously and an address field of type string. We have two instances of this struct. We have two instances of this struct. Yes, two instances. The first is a home, and it has the value IP address kind v4 as its kind with associated address data of blah 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 IP address. It has the value IP address kind v4 as its kind with associated address data. Associated address data. Okay, makes sense. The second instance is a loop back. It has the other variant of IP address kind as its kind value, v6, and has address double colon 1 associated with it. We've used the struct to bundle the kind and address values together. We use the struct to bundle the kind and address values together. So now the variant is associated with the value. That makes sense. However, representing the same concept using just an enum is more concise. Representing the same concept using just an enum Presenting the same concept using just enum is more concise. Rather than an enum inside a struct, we can put data directly into each enum variant. This is a new definition of the IP address. Enum says that both v4 and v6 variants will have associated string values. Okay, that makes sense. Oh, okay, so we can just directly type the data into this enum variants. Associated string values. Okay. We attach data to each variant of the enum directly. So there is no need for an extra struct. That makes sense. Here, it's also easier to see another detail of how enums work. Here it's also easier to see another detail how enums work. The name of each enum variant that we define also becomes a function that constructs an instance of the enum. The name of each enum variant. The name of each enum variant. V4 and V6 that we define also becomes a function. Okay. That constructs an instance of the enum. Oh, it became a function. Okay, makes sense. That is IP address v4 function is a function call that takes a string argument and returns an instance of the IP address type. We automatically get this constructor function defined as a result of defining the enum. There's another advantage to using an enum rather than a struct. Each variant can have different types and amounts of associated data. Version 4 type IP addresses will always have 4 numeric components that will have values between 0 and 255. Wait a second. There's another advantage of using an enum rather than a struct. Each variant can have different type and amounts of associated data. There's another advantage to using an enum rather than a struct. Each variant can have different types and amounts of associated data. Version 4 type IP addresses will always have 4 numeric components that will have values between 0 and 255. If we wanted to store v4 addresses as 4 U8 values, but still express v6 addresses as one string value, we wouldn't be able to do with a struct. Enums handle this case with ease. Makes sense. We've shown several different ways to define data structures to store version 4 and version 6 IP address. We've shown several different ways to define data structures to store version 4 and version 6 IP address. However, as it turns out, wanting to store IP address, wanting to store IP addresses and encode which kind they are is as common. The standard library has a definition we can use. What? However, as it turns out, wanting to store IP addresses and encode which kind they are is so common that the standard library has a definition we can use. Okay, let's look at how the standard library defines IP address. It has the exact enum and variants that we've defined and used, but it embedded the address data inside the variants in the form of 2 different structs. which are defined differently for each variant. This code illustrates that you can put any kind of data inside an enum variant. This code illustrates that you can put any kind of data inside an enum variant. Oh, even structures, okay. String, numeric types, or structures, for example. You can even include another enum. Also, standard library types are often not much more complicated than what you might come up with. So let's look at how the standard defined able address. If it has the enum and variants that we defined and used, but it embedded the address data inside the variants in the form of two different structs, which are defined differently for each variant. It makes sense. Interesting. Note that even though the standard library contains a definition for IP address, note that even though the standard library contains a definition for IP address. Note that even though the standard library contains the definition of IP address, we can still create and use our own definition without conflict because we haven't brought the standard library a definition into our scope. We will talk more about bringing types into scope in chapter 7. Let's look at another example of an enum in listings 6-2. This one has a wide variety of types embedded in its variants. Note that even though the standard library contains a definition for IP address, we can still create and use our own definition without conflict because we haven't brought the standard library's definition into our scope. Wait a second, what? This code illustrates that you can put any kind of data inside an enum variant. Strings, numeric types, or structures, for example. You can even include another enum. Also, standard library types are often not much more complicated than what you might come up with. Note that even though the standard library contains a definition for IP address, we can still create and use our own definition without conflict because we haven't brought the standard library's definition into our scope. We will talk more about bringing types into scope in chapter 7. Note that even though the standard library contains the definition of IP address, we can still create and use our own definition without conflict. We can still create and use our own definition without conflict because we haven't brought the standard library's definition into our scope. Note that even though the standard library contains a definition for IP address, we can still create and use our own definition without conflict because we haven't brought the standard library's definition into our scope. Note that even though the standard library contains the definition for our IP address, we can still create and use our own definition without conflict because we haven't brought the standard library's definition into our scope. Talk more about bringing types into scope in chapter 7. Let's look at another example of an enum in listing 6-2. This one has a wide variety of types embedded in its variants. Enum message, quit, move, write, change color. Listing 6-2, a message enum whose variants each store different amounts and types of values. This enum has 4 variants with different types. Quit has no data associated with it at all. Move has named fields like a struct does. Write includes a single string. Change color includes 3 I32 values. Defining an enum with variants such as the ones in listing 6-2 is similar for defining different kinds of struct definitions. Except the enum doesn't use the struct keyword and all the variants are grouped together under the message type. The following structures could hold the same data that the preceding enum variants hold. Let's say defining an enum with variants. Defining an enum with variants. Defining an enum with variants, such as the ones in listing success 2. Enum with variants, such as the ones in listing success 2, is similar to defining different kinds of the structure definitions, except the enum doesn't use the struct keyword, and all the variants are grouped together under the message type. The following structures could hold the same data that the preceding enum variants hold. Struct Defining an enum with variants, such as the ones in listing success 2, is similar to defining different kinds of struct definitions. Except the enum doesn't use. Oh, they are just a variance. Okay. Tuple struct makes sense. Yeah, tuple struct. But if we, where's that? But if we use the different structures, which each have their own type, we couldn't as easily define a function to take any of these kinds of messages as we could do with the message enum defined in listing success 2, which is a single type. But if we use the different structures, which each have their own type, we couldn't as easily define a function to take any of these kinds of messages as we could with the message enum defined. Oh, makes sense. There is one more similarity between enums and structures. Just as we are able to define both methods on structures using impl, we are also able to define methods on enums. Here's a method named call that we could define on our message enum. Our message enum impl and method call. Method body would be defined here, makes sense, and right, and then call. That makes sense. Message right string. So right. Makes sense. The body of the method would use self to get the value that we called the method on. The body of the method, the body of the method would use self. Okay, that makes sense. The body of the user self to get the value that we called the method on. In this example, we've created a variable m that has the value message right string from hello, and that is what self will be in the body of the call method when mcall runs. So that is what self will be in the body of the call when method when mcall runs. Makes sense. Let's look at another enum in the standard library that is a very common and useful option. The option enum and its advantage over null values. This section explores a case study of option, which is another enum defined by the standard library. The option type encodes the very common scenario in which a value could be something or it could be nothing. For example, if you request the first of a list containing items, you do get a value. If you request the first item of an empty list, You do get nothing. Expressing this concept in terms of the type system means the compiler can check whether you've handled all the cases you should be handling. This functionality can prevent bugs that are extremely common in other programming languages. Expressing this concept in terms of the type system means the compiler can check whether you've handled all the cases you should be handling. This means the compiler can check whether you've handled all the cases you should be handling. Expressing this concept in terms of the type system means the compiler can check whether you've handled all the cases you should be handling. This functionality can prevent the bugs that are extremely common in other programming languages. If you request the first item of an empty list, you would get nothing. Expressing this concept in terms of the type system means the compiler can check whether you handled all the cases you should be handling. The first of all list containing items you get available. If you request those, you get nothing. Programming language design is often thought of in terms of which features you include, but the features you exclude are important too. Rust doesn't have the null feature that many other languages have. Rust doesn't have a null feature. That is okay. Null is a value that means there is no value there. In languages with null, variables can always be in one of two states, null or not null. In his 2009 presentation, Null references the billion-dollar mistake. Tony Hoare, the inventor of Null, has this to say. I call it my billion-dollar mistake. At the time, I was designing the first comprehensive type system for references in an object-oriented language. My goal was to ensure that all use of references should be absolutely safe. My goal was to ensure that all use of references should be absolutely safe. With the checking performed automatically by the compiler, but I couldn't resist the temptation to put in a null reference, simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage in the last 4 years. The problem with the null values is that if you try to use a null value as a not null value, you will get an error of some kind, because this null or not null property is pervasive. It's extremely easy to make this kind of error. However, the concept that null is the type trying to express is still a useful one. Null is a value that is currently invalid or absent for some reason. The problem isn't really with the concept, but with the particular implementation. As such, Rust does not have nulls, but it does have an enum that can encode the concept of a value being present or absent. It does have an enum that can encode the concept of value being present or absent. This enum is option, and it is defined by the central library as follows. Problem isn't really the concept, but with the particular implementation. Okay, the option enum includes known as some variant. Okay, enum is so useful that it's even included in the prelude. You don't need to bring it into scope explicitly. Its variants are also included in the prelude. You can use sum and none directly without the option prefix. The option enum is still just a regular enum, and sum t and none are still variants of type option t. The T syntax is a feature of Rust we haven't talked about yet. It's a generic type parameter, and we will cover generics in more detail in chapter 10. For now, all you need to know is that T means the sum variant of the option enum can hold one piece of data of any type, and that each concise type that gets used in place of T makes the overall option T type a different type. Here are some examples of using option values to hold number types and string types. The type of some number is option I32. The type of some number is option I32. The type of some number is option I32. Okay. The type of some char is option char, which is a different type. Rust can infer these types because we've specified a value inside the sum variant. Makes sense. For absent number, Rust requires us to annotate the overall option type. The compiler can't infer the type that the corresponding sum variant will hold by looking only at a none value. Here we tell Rust that we mean for absent number to be of type option I32. Rust requires us to annotate the overall option type. The compiler can't infer. Compiler can't infer the type that the corresponding sum variant will hold by looking only at a non value. For absent number requires to us to annotate the overall option type. The compiler can't infer the type that the corresponding sum variant will hold. By looking only at an value. Because also none is the option T enum. It should specify that, but by just looking at none, it doesn't know. It cannot infer, makes sense. When we have a sum value, we know that a value is present and the value is held within the sum when we have a none value. When we have a sum value, we know that a value is present. When we have a sum value, we know that a value is present and the value is held within the sum. And the value is held within the sum, makes sense. When we have a non-value in some sense, it means the same thing as a null. We don't have a valid value, so why is having option T any better than having null? In short, because option T and T, where T can be any type or different types. The compiler won't let us use an option T value as if it were definitely a valid value. For example, this code won't compile because it is trying to add an I8 to an option I8. This code won't compile because it's trying to add an I8 to an option I8. Makes sense. If we run this code, we get an error message like this. Compiling so I cannot add the option I8. Okay, makes sense. So intense. In effect, this error message means that Rust doesn't understand how to add an I8 and an option I8. because they are different types. When we have a value of a type like I8 in Rust, the compiler will ensure that we always have a valid value. We can proceed confidently without having to check for null before using that value. Only when we have an option I8 or whatever the type of value we are working with, uh, do we have to worry about possibly not having a value. And the compiler will make sure we handle that case before using the value. In other words, you have to convert an option T to a T before you can perform T operations with it. Generally, this helps to catch one of the most common issues with null, assuming that something isn't null when it actually is. Eliminating the risk of incorrectly assuming a not null value helps you to be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making the type of that value option T. You must explicitly opt in by making the type of that value option T. Then when you use that value, you are required to explicitly handle the case when the value is null. Everywhere that a value has a type that isn't an option T, you can safely assume that the value isn't null. This was a deliberate design decision for Rust to limit null's pervasiveness and increase the safety of Rust code. So how do you get the T value out of a sum variant when you have a value of type option T so you can use that value? So how do you get the T value out of some variant when you have a value of type option T so you can use that value? So how do you get the T value out of, okay, makes sense, yeah. So you can use the value. The option T enum has a large number of methods that are useful in a variety of each situations. You can check them out in its documentation. Becoming familiar with the methods on option T will be extremely useful in your journey with Rust. In general, in order to use an option T value, you wanna have code that will handle each variant. You want some code that will run only when you have some T value. And this code is allowed to use the inner T. You want some other code to run if you have a none value. And that code doesn't have a T value available. The match expression is a control flow construct that does just this when used with the enums. It will run different code depending on which variant of the enum it has. And that code can use the data inside the matching value. Okay, so I can use a match expression for this option P, makes sense. So eliminate the risk of incorrectly assuming a not null value helps you to be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making the type of that value option T. Then when you use that value, you are required to explicitly handle the case when the value is null. Everywhere that a value has a type that isn't an option T, you can safely assume that the value isn't null. This was a deliberate design decision for Rust to limit null's pervasiveness and increase the safety of Rust code. Then when you use that value, you are required to explicitly handle the case when the value is null. Everywhere you are required to explicitly handle the case when the value is null. Everywhere that a value has a type that isn't an object T, you can safely assume that the null makes sense, yeah. Define whether the program could pass the compiler or not. Foo print x null foo x. Let's see, this is a function that takes a reference I32, I32 and I32 is null, and this does not compile because it doesn't have a null. 6. Consider these two representations of a result type. Type that contains a value t if a computation succeeds or an error e if it fails. The enum result 2 is considered more idiomatic than the struct result in Rust, which is not a valid reason why. Which is not a valid reason why. The enum result 2 considered more idiomatic. The struct uses more space in memory at runtime than the enum. The struct contains option types, which are only intended to wrap structs. The struct could have OK and error both be none. OK and error both be none. The struct could have OK and error both be none, while the enum must have at least one of them. The struct is more synthetically verbose to construct than the enum. The struct could have OK and error both be none. While the enum must have at least one of them. Shit. The struct contains option types which are only intended to wrap structures. The struct contains option types which are only intended to wrap structures. It's perfectly fine to have structures contain option types as fields, but if your data structure has invariants like exactly one of two optional fields should be some, then that invariant is better ensured by the use of It is perfectly fine to have structures contain option types as fields, but if your data structure has invariants like exactly one of two optional fields should be the sum. Then that invariant is better ensured by use of an enum. Then that invariant is better. Then that invariant is better ensured by use of an enum. Then that invariant is better ensured by use of an enum. Then that invariant is better ensured by use of an enum. So difficult. perfectly fine to have a structure contain option types as a fields. Uh, but if your data structure has invariance, like exactly one of two optional fields should be some. Exactly one of two. Just as difficult. But anyway, I did it.